So when you're expected to evaluate definite integrals using Riemann sums, then these summation equations come up. And they came out of precalc, but where? But they came out at the very end of the semester, and it's right before finals, and sometimes people don't remember. So I want to kind of review what induction is and where these things came from, because they're just kind of presented in calculus like, you should know this. Anyway, these are the equations that you would be using, and there's a chart in your textbook that looks something like this, and this is a very useful chart. They look a little crazy, but it makes complete sense. I think that you should try maybe a few of them, just so, try adding up the first 4 numbers, and then the first 10 numbers, and then the first 20 numbers, and see if you can figure out why these patterns work. But that's not really what we're doing with induction. We're just saying that here is the pattern, and then let's prove that it's really true. So they kind of present them to you as, they're done already. We've already thought about them. So induction is 3 steps. The first one is the base case. So you show that it works when n equals 1. And then the next thing that you do is you assume that this equation is true. And so we're going to call that the induction hypothesis. And because it's a hypothesis, as mathematicians, we can't use the same variable. So we switch out our n's for k's. And then the last thing is to prove, and it's the k plus 1 step. So that would be the next one. So if k is this step, then k plus 1 would be the next one. This is called the inductive step. And the reason why we're doing this is because if we know that it works when n is 1 from our base case, and then we can show that it works for the next one, this is the k plus 1, well, then it would work for 2, and then it would work for 3, and then it would work for 4, etc., etc. So the very first one is a little boring, so I'm going to use that as the example in this chart and then get into some more fun ones later. So this is the summation of some sort of constant from 1 to n terms, and that would be that summation is the constant times the number of terms, the Cn. So that would be like, let's say C is 4, and you're counting them up from 1 to 3. That means that you're adding up 4 plus 4 plus 4, and that would be 12, which is in fact 4 times 3, or the constant times the number of times you're adding it up. This one makes sense. So the very first thing that we would do is we use our base case. So if we plug in that n is 1, then let's see, well, C times 1 is in fact C, so that is C times 1. Yeah, it works. Base case works. The next thing we're doing, and there's a reason I'm changing colors here, is we're going to assume that it's true for k terms. So I'm going to add up C plus C plus C plus C k times, and that's going to be equal to ck. Now, the proof step is that I showed that it works for the next one. So I have C plus C plus C plus C k times, and then plus the next one, and that would be one more C plus another C. And our job is to show that this does in fact equal what would happen if we put a k plus 1 on the other side in place of k. So we know from our assume step that if I have C plus C plus C all the way up through, k number of C's, that's already ck, and then plus that extra C because we're doing this step, then I could just factor out a C, and then it's C times k plus 1, which is exactly the thing that we were trying to prove in the first place. So then we say that our induction is done. So now it gets a little bit more fun. So this is the first one, well, technically the second one we want to prove. So our base case, this is for when I have terms like 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. I'm just incrementing. So that sum, if I plug in a 1, then I have 1 times 1 plus 1, so that's 2. So 1 times 2 divided by 2 is in fact 1, so the base case works. What we're going to do is assume that this thing really is a thing. And so I'm going to replace my n's with k's while I'm making that assumption. So I have 1 plus 2 plus 3 plus blah, blah, blah plus k is equal to k times k plus 1 divided by 2. Now, it's also really important with my notation that when I write this out, I say plus dot, 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 plus, and then the k term. So my inductive step would be, I want to prove that 1 plus 2 plus 3 plus ellipses plus k plus the next one, that would be k plus 1, is equal to, now on this side we're also going to add another 1 to each of the k terms. So this would be k plus 1 now, and the k plus 2 divided by 2. So our job is to make the left-hand side look like the right-hand side. Now recall that we've already shown, or we've already assumed, that 1 plus 2 plus 3 plus blah, blah, blah plus k is equal to k times k plus 1 divided by 2. So we can just do a substitution. So we're going to replace that And so now that we have k times k plus 1 divided by 2 plus that extra k plus 1, and we're trying to show that that is equal to k plus 1 times k plus 2 all over 2. And that's the thing that gets rid of the ellipses. So now we're going to do some fancy fraction work, find a common denominator, and then with some distribution, we find k squared plus 3k plus 2, but we know that that's factorable, so let's factor that numerator. So that means that we have k plus 1, that quantity, times the quantity k plus 2, all over 2, which is exactly the thing that we were trying to prove in the first place. So now the blue things match, and we are done. Now the next one is I squared. So this is like 1 plus 4 plus 9 plus 16. We're going to add up all of the squared numbers. And we should get n times n plus 1 times 2n plus 1 all over 6. So our base case, let's see if it works when n is 1. So that would be 1 times 2 times 2 times 1 plus 1, which is 3. So if you multiply that out, you get a 6 divided by 6, and that's in fact 1. So our base case works. The next thing is we assume that this works. So 1 squared plus 2 squared plus 3 squared plus blah, 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 all the stuff in the middle, plus k squared, and that's equal to k times k plus 1 times 2k plus 1 all over 6. Now for our inductive step. So what we need to do is we need to prove that 1 plus 4 plus 9 plus blah, 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 plus k squared plus the next one, which is the quantity k plus 1, quantity squared, is equal to k plus 1 times k plus 2 plus, watch your distribution, 2k plus 3 all over 6. But we know already that from our previous step that we have assumed that the summation all the way up to k squared is a tidy little fraction. So we're going to substitute that in. Now we've gotten rid of our ellipses. Now we need to find a common denominator for that left-hand side because our goal is to try to make the left-hand side look like the right-hand side. So we're going to find that common denominator, and lo and behold, I have a k plus 1 as a common factor. Let's get rid of that. Let's factor it out so that I have a little bit easier math to work with. If I factor out a k plus 1, then I have this expression that needs to be distributed. And then when I distribute, I get the k plus 1 times this trinomial 2k squared plus 7k plus 6 all over 6. But I can factor that trinomial, and if I factor that trinomial, I get k plus 1 times 2k plus 3 times k plus 2 all over 6, and that is in fact the same thing as what we were trying to prove in the first place. So now the blue things match, and we are done. And the final one that I want to show you the proof for is the summation of I cubed. And so the summation of I cubed right here, there's a fun little exploration of why this is the same one as the summation of just I, and then we just take that answer and then square that. But that's not really the point of right now. That's kind of another fun exploration. So this, our base case, if we plug in n is 1, then I get 1 times 1 plus 1, that's 2, over 2, that's 1, squared is 1, and that is in fact equal to 1, which is 1 cubed. Now the next thing is that I assume that this summation is true. So I replace all the n's with k's so I can make this assumption. So I have 1 cubed plus 2 cubed plus 3 cubed plus all the other stuff in the middle, all the way up to plus k cubed. My notation is important here. And that should be equal to k times k plus 1 divided by 2, all of that quantity squared. Now for my inductive step, then we have everything, 1 plus 8 plus 27 plus all the other cubes all the way up to k cubed plus the extra one, k plus 1 quantity cubed. And that's supposed to be equal to, now increase the right-hand side by 1, so I get k plus 1 times k plus 2 divided by 2 and all of that squared. But we know from our assumed step that everything up through k cubed is going to be this tidy little expression in fraction form. So I can just do a substitution. And when I do the substitution, I need to find a common denominator. So I'm going to call that 4, or 2 squared. I'm going to write it both ways, like that. And then instead of having a k plus 1 as my common factor, this time I actually have a k plus 1 squared as my common factor. So let's factor out k plus 1 quantity squared. And then when I do that, I have what's left over in the other set of parentheses, or in this case brackets, I have k squared plus 4 times the quantity k plus 1, which is the same thing as k squared plus 4k plus 4. Now, I know that factors nicely as k plus 2 quantity squared. So now I have k plus 1 quantity squared, k plus 2 quantity squared over 2 squared. And since everything is squared, I could just rewrite it nicely as k plus 1 times k plus 2 over 2, all of that squared. And that is exactly what we're trying to prove in the first place. Now, even though you may get them in the factored format, it is my opinion that the expanded polynomial is actually going to be much more useful to you. And so I think you should recognize the factored form, but then also you need to be able to swap that out for the expanded form. Let me show you what I mean. So I didn't want to copy out of the textbook because I didn't know if that was a copyright issue, and I couldn't get ChatGPT to say it in the notation that I was telling it. So this is in my own handwriting. This is the kind of thing that you're going to see when you evaluate a definite integral using a Riemann sum. Now you can go through the math of this later, but this is more of an in-class kind of thing. This is the calculus part. We're talking about, the pre-calculus fun stuff. So right here where my fingers are, that's where that substitution is going to be. You see the summations with the i's in them, they swap out for things with n's, and then because they are equal, then you can finish that problem. So the other thing though, and here is a step that's not in your textbook, but it is my opinion that it should be, is right here. And what's happening is I'm using the expanded form of the polynomial, with n in it, instead of, so I'm using the one from the third column instead of just the one from the second column. And that is what's missing in the textbook, and I think you really need that one in order for this to make sense. And then after that, then your limits as n approaches infinity, that makes a whole lot of sense, and then you can get to where you're going with this. So it is my recommendation that you do that.